Hey everyone, and welcome to today's Explainer. We've got something super excited lined up. We're going to dive deep into the real logic behind gate problems. Specifically, we're decoding this completely notorious question from the 2014 GATE computer science exam. If you've ever stared at a number system problem with unknown bases and just felt totally intimidated, well, you're in the right place. We're going to break this whole thing down step by step and turn what looks like a complex mystery into, honestly, absolute clarity.
Okay, so take a look at this. 312 base x divided by 20 base x equals 13.1 base x. Wow. Talk about a hook, right? I mean, it looks pretty intimidating. We've got this totally unknown base x, and just to make things, extra fun, there's a tricky little decimal sitting right there in a non-base 10 format. It's the kind of thing where when you see it on an exam, panic can definitely set in. But seriously, don't worry. The logic we're about to uncover here is actually incredibly elegant.
Section 1. The core decoding logic. Let's get right into it.
The real secret to crushing these types of gate problems, it really isn't about memorizing a bunch of formulas. It's about understanding the core decoding logic, right? Knowing how to rip the disguise off that unknown base. So if you remember literally just one thing from this entire explainer, let it be this, our golden rule: convert everything to decimal. Think of base x as like an alien language. To understand what it's saying, we just have to translate it back into our native mathematical tongue, which of course is base 10. Because once we're in base 10, standard algebra takes over, and we are completely back in the driver's seat.
Moving on to Section 2, translating to base 10.
All right, armed with our golden rule, let's just systematically tear this scary equation apart, piece by piece. We're going to translate the numerator, the denominator, and then that result on the right side. Let's kick things off with the numerator, 312 base x. We need to expand this into a polynomial using positional multipliers. You've probably seen this before. Starting from the right, that 2 gets multiplied by x to the power of 0, the 1 is multiplied by x to the power of 1, and the 3 gets multiplied by x squared. Add all those up, and our alien number suddenly turns into 3x squared plus x plus 2. See? Already looking way more familiar.
Next up, the denominator 20 base x. We follow the exact same logic here. The 0 is multiplied by x to the power of 0, which, just completely disappears. Then the 2 is multiplied by x to the power of 1. So this whole piece neatly and wonderfully simplifies down to just 2x.
Now, what is really interesting about this next part is how we handle the right side of the equation, 13.1 base x. The digits before the decimal, the 1 and the 3, they just follow our standard positive exponents, right? Giving us x plus 3. But that 0.1 is the curveball. Because it sits past the decimal point, it actually dictates a negative exponent. We have to multiply that 1 by x to the power of negative 1, and that is exactly the same as writing 1 divided by x.
And look at this. This perfectly shows how our initial golden rule logic has completely transformed the whole problem. I mean, we started with the confusing base radix equation that basically looked like nonsense, but by systematically translating it, we've turned it into a recognizable, albeit slightly messy, algebraic equation. We've got 3x squared plus x plus 2, all divided by 2x, equaling x plus 3 plus 1 over x.
Which brings us to Section 3, solving the algebra.
Okay, this is where it gets really good. We're at the climax of the problem now. The translation phase is totally over, and it's time for pure algebra. We just need to simplify the math to find our unknown x. The very first step? Clean up that messy right side. We have x plus 3 plus the fraction 1 over x. By taking the least common multiple, the LCM, which is simply x here, we can combine all these terms. X times x is x squared, 3 times x is 3x, and the 1 just stays exactly as is. So the entire right side becomes x squared plus 3x plus 1, all divided by x. We are setting up something incredibly satisfying here.
I absolutely love this quote from the instructor in our source material. They said, "X ne X cum murder kerdia," which playfully translates to X murdered X. And it's so true. If you look at our equation right now, we have a 2x in the denominator on the left and an x in the denominator on the right. Those x's beautifully, perfectly cancel each other out. They literally eliminate each other from the equation entirely.
So with the x's officially murdered, we're left with just a single 2 in the denominator on the left side. We just cross-multiply that 2 right over to the other side. Multiply it by the x squared, the 3x, and the 1. Boom! This sets up our final algebraic showdown,
3x squared plus x plus 2 equals 2x squared plus 6x plus 2. From here, guys, it's just standard cleanup. We're going to bring all the terms over to one side. 3x squared minus 2x squared, that leaves us with just x squared. We have an x and we subtract 6x, which gives us negative 5x. And look at the constant 2. It's on both sides. So those completely cancel each other out to 0. We are left with this beautifully simple, elegant quadratic equation. X squared minus 5x equals 0.
If we factor out the x, we get x times the quantity of x minus 5 equals 0. This gives us two possible mathematical answers, or roots, either x equals 0 or x equals 5. But wait, remember the logic of the problem we're actually solving. We're looking for the base of a number system. You logically cannot have a base of 0. It just doesn't exist in this context. Therefore, 0 gets immediately rejected.
And this brilliantly illustrates our final answer. The mystery base x is exactly 5. Seriously, by just trusting the logic, converting everything to decimal, and carefully stepping through that algebra, we took a highly complex gate problem and systematically dismantled it, right down to a single digit. How cool is that?
Section 4. Master Strategies for Gate. Let's pull back a bit. You know, the real value of this explainer isn't just in solving this one specific question, it's about broader exam mastery. How do we take the logic we literally just learned and apply it to future challenges? Well, here are your absolute crucial rules. First, whenever you see an unknown base equation, always convert it to decimal. Just make it a reflex. Second, understand the exact format of your question. If it's a numerical answer type, an NAT, where you actually have to type in a number, you've got to push through the algebra exactly like we just did. But third, if it's a multiple choice question, you've got a massive shortcut. Once you set up that base 10 equation, you can simply plug the multiple choice options right into it to verify which one balances it out. It's an absolute game changer for saving time.
We've really seen how powerful the right structured approach can be today. The unknown becomes known, the totally intimidating becomes completely manageable. So I want to leave you with this final thought to ponder. Armed with this logic, which base radix problem are you going to demolish next using the golden rule? Thank you so much for joining me for this explainer. Keep applying this logic, stay curious, and I'll see you next time.